Wonderful. Okay, so we are delighted, really delighted, honored, and very, very grateful to have Petja Paakkinen here to give the second of the two talks. Just as a quick reminder, so Petja received his PhD from the University of Jyväskylä in 2019, 2 years as a postdoc at Compostela, and is back at Jyväskylä as a postdoctoral researcher, and is one of the authors of EPPS16 and EPPS21. And really looking forward to hearing about nPDFs, status challenges, and new probes. So please take it away when you're ready. Thank you.
Yeah, thanks a lot. Pleasure to talk to you again. And let's go straight to the business. I have plenty of slides, so let's go. Let's see how far I get with this. And of course, again, anytime you have any questions, please ask. And last time or last week we discussed about PDFs and nuclear PDFs and why do we need them and what is the basic status of what we know about them. And this week I was planning to go into more detail about the different recent data that have been included in the global analysis. And just to start, so the basic idea in this global analysis was that we use just the QCD collinear factorization to obtain the nuclear PDFs by fitting to a large set of data, and this gives a kind of a model agnostic way to study the nuclear effects. And yeah, then I left you kind of with this. So we have many recent new analysis, and basically the situation is such that we know the U and D valence quarks quite well. So large X region, maybe down to 10 to minus 2. We know how the U and D quarks behave quite well. Then at smaller X, we start to have some uncertainties, particularly at smaller scales. But in any case, the situation is quite good. And we have good agreement between the different fits. But then there are some flavors where the situation is not as good. So I discussed a bit about the gluons, where, well, we all see the similar shapes in the results of the global fits. So it seems like we have some shadowing in the gluons, but how much exactly varies a bit from fit to fit. And then also there are some differences in the large X behavior. And then for some flavors, well, strange quark is just the most difficult at the moment to fit. We don't have data which would just really pin down where these modifications are. And so there are large differences between the different nPDF extractions. And why do we actually see these kind of differences? Well, this is partly related to what data are included in these fits and how. So the current situation in the nPDF world is that most of the studies that are performed are at the next leading order in QCD, perturbative QCD. There are some studies which go one step further to next to leading order, but the amount of data in these studies are still a bit limited. Or rather, the amount of different data types, they still have like a couple of thousand data points included, which is like a 2000 bit above is the current standard. And what this kind of large data sets tell us is that the collinear factorization seems to be working very well. So we get very good fits to large set of data, and it seems that we have a collinearly factorizable nPDFs which satisfy our theoretical framework and that are universal from one process to another. So this is like a big victory for the framework. And but then we see these small differences, and this is kind of natural to see because we are parameterizing these nPDFs in different ways, and so this is where some of the differences come from. So we have different number of 3 parameters in the fit, and what aspects of the fits they govern can differ. So this is one where the differences come, and the other is what data and how these have been included. So I thought I would start with the heavy quarks, which have been included in the recent EPPS21 in nPDF 3.0 and in the NCTEC15 HQ fits. And what I signaled here is that the way these are included in the fit differ a bit. So let's go into that detail.
I'm sorry, before you continue, could you just, maybe just briefly, if you could, why did EPPS not include, it seems like some p-lead data on pi0, pi plus minus, k plus minus, and then p-lead gammas? So that's just one question. And then the other question, why does KSASG have twice as many data points, but it looks like the same data sets as, say, EPPS and some of the other and PDF?
Yeah. So starting with the EPPS21, well, we concentrated in this fit with the digest data set because this is like a very constraining in large section of X, and it seems like it's more constraining at the moment than any of these pion and kaon production data. These were included in the NCTEC15 fit, however, so it would be possible, but we just well haven't had both the time and then we know that the what we would gain is not so large a reduction in our uncertainties because we have this digest data. And the same applies for the direct photon production. So the data sets that we have they have quite large uncertainties. So it would not give us very strong additional constraints. Then for the KSASG, they have a very large set of data from neutrino nucleus DIS data sets, and now I need to kind of remind myself. So we currently in EPPS21 only include the Horus data set, and there is in particular this NUTEV anomaly. So not all of these data seem to be like very consistent with other data, but it's been a while since I paid attention to this, and it would be possible to include more data from this also for us, but we've only been using the chorus, so there comes a difference in how much data is included.
Super, thank you. It's interesting to hear all of these subtleties that we wouldn't really have known about otherwise. Yeah, thank you.
Exactly, and there are a lot of like these small things which then can in the end cause small differences in the fit results.
Mm.
And then also the cuts that people use for their data, they vary. So some people are more cautious about how large Q-squared we want to require for our data sets. And this also can enlarge or narrow the amount of data points that are included in the fit.
Mm.
Okay, so let's go to the heavy quark production. And here for the heavy quarks, we have different ways how the production of these can be described. One of the most simple ones is this fixed flavor number scheme, where the heavy flavor is not included as a parton in the PDFs, but rather it's always produced at a matrix element level. So, and the nice thing about this scheme is that it's very easy to include the mass terms for the heavy quark. It just appears in the matrix elements, and that's all. Everything works fine. And this works very well when your PT is small, but then once your produced heavy quark flies off with a larger PT, you start to have these logarithms of PT over mass, and then you start to the applicability of this scheme starts to be questionable. Then on the other extreme, if we consider high PT production, then we can describe this with the zero mass variable flavor number scheme, where then you neglect the heavy quark mass because you have large PT, which is more important than in this process, and then you include the heavy flavor as a parton and allow it to be produced also in the initial state radiation and in the final state radiation. But then, since the mass terms are neglected, this method doesn't work in the small PT region, and you can even have divergences because there is nothing regulating the collinear splittings. So then we would like to combine these two things, where at a small PT we would have something resembling the fixed flavor number scheme, and then at higher PT the zero mass variable flavor number scheme. And this is done by means of so-called general mass variable flavor number schemes. There you include both of these, but just doing that would end up in double counting, since part of this splitting here was already included or is part of the PDF of this heavy flavor. So then you need to add these subtraction terms, which then remove the double counting. And also importantly, this framework includes gluon to heavy flavor fragmentation, which can provide a large contribution to the cross-section in heavy flavor production. So if we then apply this with the data sets that we have, like LHCb D0 production, this general mass scheme has been used in the EPPS21 fit. And as I discussed last week, we get a large reduction in the nPDF uncertainties when we do this. So these are very important constraints for the nuclear gluons. Now, the same data have been included also in the nPDF 3.0 fit, but their approach is a bit different. They use a Pauhek plus Petja event generator for their theory calculation. So again, they get very good reduction from the initial prior uncertainties when fitting this data, going from this large blue band to this smaller green one. But what they find is that they have actually quite large scale uncertainty in the calculation, which is present both in the forward and backward data set, and seems to be like a dominant one for the backward data. So that's why they fit only the forward data set. Whereas, well, similar scale uncertainty is not seen in the general mass scheme that was used in EPPS21. So we have a different theoretical description of the same data set, and of course, when we do that, this can lead to small differences in how the data or what kind of constraints the data then end up giving for the nPDFs. Now then, NCTEC 15 HQ uses yet another approach. So in their framework, they use this data-driven approach where they fit first the matrix elements to proton-proton data. So they parameterize the parton level scattering probabilities using 2-to-2 kinematics and only including the gluon-gluon contribution. And then once they have fitted these matrix elements to proton-proton data, they use these obtained matrix elements for fitting nuclear PDFs with the proton-lead data. And again, in their paper, they show that they get very nice reduction from the previous NCTEC 15 fits, go into this smaller red band when including the heavy quarks. But again, well, this is kind of a very simple way, since you do like heavy assumptions about the 2-to-2 kinematics and not including the initial state quarks. So this is maybe not so much QCD driven, of course inspired by QCD, but then more like a, well, data driven approach. So then again, since you use different theoretical framework, you might end up with different results for your nPDFs. And one should really keep this in mind when comparing with new data. So for example, we have now D0 production data from LHCb at 8.16 TeV. But these data have so far been compared only with the matrix element fitting results. And so before we draw any strong conclusions about this, we should actually do more PQCD oriented calculations and check whether these differences between the data and predictions actually hold also there. So this is still work in progress. Okay, I think this was what I wanted to say about the heavy quark. So if you have questions, please go ahead before I move to other aspects. And if not, then I'll move to W bosons, because here we have again very nice data from LHC. In this case, I'm showing the CMS results at 8.16 TeV, And here, the electric bosons are, of course, important probes of the flavor separation, and could provide new constraint for the strange quark, for example. But then again, you could use this data in different ways. So, for example, NC15 and nPDF, they use directly these absolute cross sections for proton-lead data. Whereas in EPPS21, we use nuclear modification ratios in order to cancel proton-PDF uncertainties. And the motivation is that if we look at the absolute proton-lead cross sections and ask how much of the uncertainties in our PDFs come from the free proton degrees of freedom and how much from the nuclear modifications, we see that the proton PDF uncertainties are an important part of the absolute cross sections. And then what we try to do when constructing different ratios is that we try to cancel the proton PDF uncertainties, and this works pretty well for the proton-lead cross-section ratio that we use. But still, we see that we might have some sensitivity to the proton PDF still, and this could become an issue when we go to yet larger data sets and more statistics in the LHC round 3. So to tackle this problem, we have started to propagate the uncertainties from the proton PDFs in our nuclear PDF fit. So usually in our fits, we have been doing so that we take the central set, so the best fit of proton PDFs from the baseline that we use, and then we just fit the nuclear modifications on top of that using the full data set that we have. And that would provide us the central set of our fit. And then we do a Hessian error analysis of these nuclear modifications, so varying the parameters, seeing how large increase in the chi-square that causes, and then that gives us a reasonable region of where we think the description of the data is good enough that this kind of variations in the parameters is okay. And this provides us with the nuclear uncertainty sets. But now, on top of that, we have taken all the error sets of our free proton baseline and fitted the nuclear modifications for them. So this would give us then the contribution from the uncertainty in the free proton PDFs on our nuclear modifications. And then we combine these two sources of uncertainty, we get the full uncertainty of our nuclear PDFs. And also nPDF have used a somewhat similar approach in their case with the Monte Carlo framework. Now, then what happens is that once you start to do this, your nuclear modifications that you obtained and the proton PDFs are correlated. And so now you start, if you remember my talk last week, I said that then the nuclear modifications are used currently in the proton PDF sets in order to get better constraints on some flavors like strange. So this is starting to become a really convoluted problem where your proton PDFs affect your nuclear PDFs and the nuclear PDFs affect your proton PDFs. And so this is still an issue that needs to be solved in the future. How do we actually do this fits such that we are like really paying attention to all the theoretical uncertainties that go into our fits? And since in our results we see that the, let's say, gluon PDFs of the, or the gluon modifications and the gluon proton PDFs are somewhat correlated, and the same applies for strange, we can conclude that your choice of proton PDFs can affect what kind of nuclear modifications you get. And so this is going to be more important in the future when the data uncertainties go down. So then the uncertainties from theoretical sources become more important.
Let me throw a question in here.
Yeah.
Is this cross pollination that's going on more pronounced in certain regions of X, or?
We haven't been studying this very much in detail. So this is one of the few plots where about the correlations that I have plotted.
Mm-hmm.
So you can see that here we have some X dependence. So at large X, or in this region of like anti-shadowing, we see that there is a bit of anti-correlations with the nuclear modification in gluon and with the proton PDF, and then in the shadowing region it seems to be the other way around, that there is a positive correlation. But well, this is like some the correlation factor is not very large, so so yeah, there seems to be that how it goes can well depend on the X, but we have not studied this in very much detail, seeing how it behaves in all aspects. But
I'm kind of asking this because, of course, at some point you would expect that there are some tensions that come in because at very small X logarithms get large, and sort of kind of asking whether you see any place where you see this sort of tension creep into the questions that you're asking at the moment. But maybe I'm pushing ahead in your talk in some way. So
no, it's a valid question and a very good one. But currently, I maybe wouldn't say so, because, for example, in the forward direction, the data gets very well described, but we maybe see some places where perhaps here with the W data, we would kind of want to have a it's hard to say. If we had a bit less shadowing here, then due to normalization uncertainties, we would get a bit better description of the whole data set. So it's about this. We see some small differences, but then it's
nothing glaring. Okay.
Yeah, it's somewhat difficult to say where then these originate, because it can be there can be multiple factors in place. So whether it's the proton PDFs that we use, or indeed some like logarithmic effects that come into play, or since these are NLO fits, maybe we need to go to NNLO, and that's actually what I was about to discuss with this Z production, because this is something where we see a bit of a mismatch between the data and the nPDFs. So if I start with the large mass data set, we see this kind of behavior where the data are below our predictions at backward rapidities, but when we then go to forward rapidities, then the data are above our predictions. And currently, we don't know why this happens. It's a bit of a strange behavior that there is a kind of a jump at mid rapidity, changing from one kind of a behavior to another. And this also happens with the nPDF 3.0 fit. Maybe, well, it's not exactly the same. Again, they are plotting or fitting the absolute cross sections, and we are using this nuclear modification ratio. But again, in forward direction, the data is above, and then you see at least some of the data points at small or backward rapidities are below the prediction.
Oh.
And then once you go to the small mass data set, you see that the data points are again above the prediction. And this has been discussed that this is most likely an next to leading order effect. So if you would include those corrections, your prediction would go up. And this could like explain why we see this kind of not so good description of the data. The chi-squareds that we get are, well, not ideal, but still not outrageous. So this is like one of the cases where we see small tensions, and we would like to get a better handle on this in the future. But currently, it's very hard to say where these small differences originate from, because there are multiple aspects like the proton PDFs, the NNLO corrections, and stuff like that. But all the time, we need to pay attention to these small details and try to understand better how we could like improve our description of the data, what might be the aspects where we need to improve. And last week I pointed out also one place where we don't really know what's going on, and it's these very forward data points of the digest production in the CMS measurement, where both us and nPDF, they find that the data are just strongly below the prediction. And since these are like double ratios, and also already quite a lot like systematics dominated uncertainties. Maybe I shouldn't say dominated, but the systematics come to play in this measurement. So they have large data sets. Then maybe it's due to some missing data correlations, or like we would like to include the data correlations in our fit, but we don't have them. So we don't know whether whether our fit would then prefer a somewhat different shape when we included these data correlations. Or maybe this measurement is sensitive to some of the next to leading order corrections. The NNLO calculations for digest production have been around now for a couple of years, but they are private codes, so we don't know yet whether this would help describing the data if we had them available. Or maybe there are some non-perturbative effects that we have not included, like the hadronization corrections, which we have said that these cancel in the ratio that was measured. So again, small details which we need to pay attention in the future, because we get good description of like a couple of thousand of data points, but there are some places where the description is not so good. And yet another case, quite recent one, was this pion production data from LHCb. So when we look at the forward direction, we see that our nPDF calculations agree with the data very well, no problem. And also the inclusive hadron measurements agree with this pion data. There are some small differences which can be understood by the different collision energies. But in any case, in the forward direction, everything seems to work just fine. Then when we look at the backward direction, now the story changes. First of all, there seems to be some enhancement in the inclusive hadron data compared to just pion one. And this could be understood as heavier mesons and baryons, which are we don't have proper fragmentation functions for describing this, and maybe there are additional production of these baryons which is not so well describable in these small PTs with the collinear factorization. So if we just saw that there is some enhancement in the inclusive hadrons, that would be okay to us, so to say. But now we see that there seems to be some enhancement in the pion data that we don't see in our nPDFs. And this seems to be in the region which is traditionally understood as where the Cronin effect sits. So maybe there is in this, I would call this still quite small PT range. So maybe in this small PT range, we have additional higher twist corrections, which would need to be taken into account in order to describe this data. And then the question to me that I would like to study in the future is how small in PT can we actually go such that our description of the pion production works fine? Because we have very good data nowadays from different experiments for this process, and so we could I think we would be able to study this systematically. So the question would be, how large in PT we need to go such that collinear factorization is it would be working very, very good. And then we can ask about the questions, okay, what's then happening at smaller PT? Is there some additional effect or maybe not? And well, this is not the only place where we see something like this. Phoenix had also some new data set where they now study have a small system scan of the pion production. And what they found out was that the Cronin peak again follows a different ordering than what we would expect from the nPDF calculations. So in their measurement, the peak at again around maybe 4 GeV is smaller in helium-3 plus gold than it is in deuterium gold and proton gold. And this goes against the predictions from nPDFs. And they also discussed in their paper that maybe this is some multiple scattering effect or maybe some flow-like component, which could also affect our observables in small PT range. And also in the high PT region, the measurement is below the predictions, but one has to pay attention to the large normalization uncertainties in this data set. But if we would now, since we have all the jets and stuff included in our global fit, we could now pay more attention to the hadron production and see how well these fit in our framework. So at the moment, I wouldn't claim that, well, collinear factorization doesn't work, but maybe we now have an opportunity to really go into details, see where it might break down. Is something like a couple of GV, like 2, 3, is it just too small in the nuclear environment? Maybe there are then higher twist effects that need to be taken into account in this small PT range. Okay. Then also something that is a problem in our fit is that we don't always have the data that we would like to have. And for DIS measurements, the situation is quite okay. We have good amount of data from different nuclei ranging from helium-3 all the way to lead-208. But these are only fixed targets, so EIC is very welcome here. Then for trillion measurements, situation is a bit worse. So we have fewer data sets, and the number of different nuclei where we have them is smaller. But the problem is that these kind of, pion production jets, for this we have only data at heavy nuclei plus then this proton aluminum data set from Phoenix, but nothing else. So it would be really good to have more data in order to constrain how our gluons or the gluon modifications evolve in nuclear mass. And one opportunity that I studied some time ago was whether we could use digest production in the proton-oxygen run, which we are expecting to happen during run 3 at the LHC. And what I found was that, okay, it seems to be that we might be able to have a single differential measurement there. So given the expected luminosities, we could have just enough events that we could have small enough statistical uncertainties to give new information on our nPDFs. But again, the problem is that if we just have the proton-oxygen data, then large part of the cross-section uncertainties in our predictions come from the free proton PDFs. And then it's harder to disentangle the nuclear modifications. And another problem is that we don't expect to have a proton-proton reference at the same energy as we expect to have the proton-oxygen data set. So then, yeah.
Why are there such large uncertainties in the forward and backward? In the forward and backward region, you see very big error bar.
You mean for the projections, or?
Yeah, like just the rapidity of 3 and -3, I see just big error bars.
Yeah, so you mean this data?
Yeah.
So it just originates from having smaller number of events. So the cross section goes down. So then you have fewer events, and then once these are like ratios. So then you see the relative uncertainty grows when you have fewer events. And these are just projections, so like pseudo data and not even randomized with respect to the nominal value. Okay, but then if we study this kind of a mixed energy ratio, taking proton-oxygen data at some energy and proton-proton at a bit smaller, bit higher, would this help? And it seems that it would. So if we would have this kind of a measurement of the nuclear modification ratio of proton-oxygen and proton-proton at bit different energies, that would be just fine. And these are now a bit older nuclear PDFs because new ones appeared after this study, but still we could expect to see that the data could provide us new information about how the nuclear effects evolve in the nuclear mass. So in this sense, I'm really looking forward to what data we will have from run 3. I think we are going to learn a lot of new things about the nPDFs. And okay, if you have any questions, please ask now. Then I'm going to switch topic a bit. So, because
Do you have an explanation why that moving these things apart doesn't spoil your cancellations badly? You have sort of
yeah, so it's just that the difference in energy is small enough. So once you increase the energy, you are probing smaller values of X once you take the same energy jet. So it seems like this shift in X is just small enough that there is not too much happening there. And so even though you might be probing then the proton PDFs in your proton oxygen dataset at a slightly different value of X compared to the proton-proton, the difference is small enough that your uncertainties in this just cancels out. So, but it's like only if we have a small enough difference. If we would go some like very different energies, then I'm expecting that this would break down.
So I should think of this as a log of the ratio, something like this.
I'm not sure. I don't know. Maybe if you open up a bit more what you mean.
Yeah, no, I need to think about this a little better
Okay.
before I actually ask a better question.
Yeah, sure. Okay, then what I was planning to discuss still, if you have time and interest, would be these new possible constraints from UPC processes. And this is something that has gained a lot of attention in the recent years. So in these UPC events, the term comes from ultraperipheral heavy ion collisions. The two nuclei are passing each other at an impact parameter larger than the sum of the radii of the nuclei. So then there is no hadronic collision between them. But on the other hand, one of the nuclei can interact with the electromagnetic field of the other, and at higher energy, this can be described in so-called equivalent photon approximation. So then we get access to new photonuclear processes, which could tell us new things about the nuclei. And one proposed observable is the exclusive UPC J-psi photoproduction. And there has been recently very good progress in this. So there has been NLO calculations now applied to the UPC lead. And well, this new approach seems to be able to describe the data that we have very nicely without any ad hoc corrections or like normalization. So this is good, but then there are a couple of problems. So first of all, there seems to be very large scale uncertainty all still at next to leading order. So then we need to ask, is the perturbative convergence good enough that this could be actually used as a constraint of the non-perturbative constituents or non-perturbative object that enter our calculation? And then another question, actually, are these nuclear PDFs that enter there? And we know that, well, it's not directly so, but instead in these exclusive processes, you are actually probing the GPDs, so generalized parton distribution functions. And then you would need to have a mapping between these GPDs and the nuclear PDFs if you wanted to constrain your nPDFs. So a lot of theoretical uncertainties here. Another process which could be used in principle is then more inclusive one. So let's say dijet production in UPC processes. And this can happen in two ways. There is a direct component where one of the nuclei emits a photon, which then directly interacts with a parton in the hard scattering from another nucleus, and this produces a jet pair. Or the photon can be resolved, or its partonic content can be resolved, and then the interaction is between a parton from the photon and a parton from the other nucleus. And recently, the Atlas collaboration has unfolded their dataset on this, and we are now expecting a final dataset and the first full measurement of this cross-section. So then we would be really interested to see if we can probe the nPDFs with this data. And well, next I was going to show you something that I'm going to present at the Quark Matter conference. And this is related to the approximations that we use when describing this data. So previous NLO predictions have been performed in so-called point-like approximation. And I've had this question in mind that can we or should we actually do better than that? And to discuss that, we need to go a bit into the collision kinematics of the UPC dijet production. So in this case, let's begin from this impact parameter view of the collision, and then the cross section can be described in this convolution formula, where the ingredients are that we have a nuclear suppression factor, which tells about the probability of having no hadronic interaction at a certain impact parameter. Then we have the flux of photons from one of the nuclei at some radius from the emitting nucleus. And then also in the resolved case, we need the photon PDF. Then we need the nuclear PDF, but now these two vectors R and B do not actually need to be the same. And then we see that we need to take into account that the photon which was emitted from nucleus A interacts with the nucleus B in some point at radius S from the center. And then we have the partonic cross-section, which tells the production rate from these partons that we have. Now, why this impact parameter picture becomes important is that, okay, if we have the two nuclei far enough apart from each other, so discussing now as a function of R, if we have a large enough R, then the collision configurations that we have are all allowed. There is no nuclear overlap between the nucleus A and B, and so any S is equally allowed. But if we go to smaller r, this doesn't apply anymore. So some of the collision configurations at fixed r are going to lead to UPC events. But in others, we have a nuclear overlap, and so these would be non-UPC collisions. So then we have a restricted phase space in S for the UPC events. And this is something that I've been studying. So now if we assume that we can factorize this nPDFs depending on the location in B, in terms that we have this nuclear thickness function multiplying the traditional nuclear PDF, then we can write the cross-section in this usual convolution formula where the effective photon flux now includes all the two-dimensional integrals. And this was done in the Atlas paper, where they use this kind of way to reweight their Petja predictions. So if we now start from very basic assumptions and go to more complicated ones as we move on, well, here on the left-hand side, I'm showing the real photon flux from a point-like source. And then on the right-hand side, I'm showing this effective flux. In this case, we are using this point-like approximation with a sharp cutoff at some radius r, or some impact parameter r, b, but since we are also taking the nucleus B to be a point-like object, then R and B are just the same. So this is the most simple approximation one can use, and it was used, for example, by Guse and Claassen in their paper. And then you have this traditional form of point-like effective flux at some minimum impact parameter. Now, if you want to do better, one thing you could try and do is that you, instead of using a point-like flux, you use that from a Wood-Saxon source. Well, this impacts the flux only at very small values of R. So if you still use the hard cutoff, this doesn't make any difference. But you could also improve your description about the nuclear overlap, so and take into account the like the finite size of the nuclei and calculate the this gamma suppression factor from the Wood-Saxon distribution. And if you apply that suppression factor, then you see that your effective flux as a function of R is a bit different, but no huge difference. Okay, but we could try and do still better. So what we have still taken the nucleus B to be a point-like object, so R and B are just the same. Now, if we relax that assumption and take into account the finite extent of the nucleus B, taking it from Wood-Saxon distribution, then we see that there is additional contribution now coming from smaller r. So this convolution in the gamma suppression factor and the nuclear thickness function in nucleus B is changing how this effective flux behaves as a function of R. And it seems like accounting for this S dependence is important in the small R region. And here we can kind of separate two regions. So in this like large R region, we are in this far passing scenario where the point-like approximation works just fine. But now for the dye-jet production, where we have high PT jets, the photon energy needs to be high enough. And if we go to higher photon energies, then we start to see that there is a large contribution coming from these near encounter events. And well, how large, this is something that we want to find out. So now on the left-hand side, I have the effective flux now integrated over all the angular variables in these three different scenarios: point-like, the Wood section where we still took the nucleus B as a point-like, and then the full Wood section calculation. And on the right-hand side, I have the dye-jet cross-section at NLO calculated with GRV photon PDFs and EPPS21 nuclear PDFs. And then on the lower plots, I'm showing the ratio of the how large part of the flux or the cross-section comes from the near encounter events compared to the total cross-section or flux. And what we see is that at small photon energies, well, most of the flux comes from these like far passing events. But once we increase the photon energy, we require more, or when we require more energetic photon, then these must originate from the events where the two nuclei are close by. And then we are sensitive to these near encounter events. And this is also what we see in the cross section. So at the largest measured values of Z gamma, something like 80% of the events are these near encounter events. And well, how much of an effect then these calculations or different approximations of the effective photon flux, then how large the effects are, where, well, there can be some effects from which approximation we use. So now taking the ratio to point-like approximation, if we would have used the Wood-Saxon but with a point-like target, then there would be kind of a large separation between these. But then the full Wood-Saxon calculation has yet another effect. So what we see is at maximum something like 10% effect comparing the full Wood-Saxon calculation to a point-like one. So this is and the effects from the nPDFs that we expect are something like 10 to 20%. So then it seems like it's actually necessary in the dye-jet production case to really take into account these geometrical effects. And well, this leaves me still with some questions. So in all of this, we assumed that we can factorize the nuclear PDFs which depend on the location within the nuclei in terms of the traditional nPDFs times the nuclear thickness function. But this is just a simplification. Maybe we should use the impact parameter dependent nPDFs instead. And also, well, if this is the case, that we are probing the impact parameter dependent nPDFs here in an inclusive process, how are actually these objects related to the GPDs that are extracted from the exclusive processes and which are like Fourier transforms of the impact parameter distributions. So I think this is very interesting thing that should be studied. And one caveat yet is that here we have neglected the possibility of electromagnetic breakup from Coulomb excitations of the passing nuclei. And to directly compare with the data, we still need to take into account this in our gamma AB suppression factor. So there is still some work to do in this front, but I think these results are very interesting. And now you got a little peek to my talk in Quark Matter next week. So I'm happy to hear your comments on this. So thank you.
Okay. Super. So floor is open for questions. Dan, please go ahead.
I just have a question on that very last point that you made. I don't quite understand what you mean with electromagnetic breakup. What does that actually entail with these two nuclei passing each other? Like literally they're breaking apart, or?
Yeah, so what happens is that when the two nuclei pass each other, there is of course the possibility that they interact hadronically, like in non-UPC processes, or then you have some UPC process where the photon from the field of one interacts with the photon of, or one of the nuclei interacts with the photon from the electromagnetic field of the other. But this is not the only possible way that the nucleus can interact with the electromagnetic field. So this would be so this hard scattering is not the only possibility. But there can be the nucleus can have multiple interactions with the photons of the other field. And then these more likely small energy photons can excite the nucleus, and then it can break apart. So yeah, so in these digest events, what happens is that one nucleus is the photon emitter of the hard interaction. So then the other nucleus goes into a hard interaction with the photon from the other, and then the emitting nucleus just flies into the beam pipe. And this is like the event selection that is used in the measurement to tell that this was an UPC process.
Okay, yeah.
But it is possible that this nucleus would be excited by the electromagnetic field of the other nucleus, and then it would actually break apart or emit a neutron. And this would then not fall within the event selection that is used in the measurement. But currently in the calculation that I showed, this possibility is not taken into account. So in order to compare with the data, this still needs to be done.
Okay, thank you.
Yep.
Maybe just to follow up for me, so you say hadronic interaction suppressed. So I'm trying to think this through. So we think about the strong force, and the strong force is localized to certain distances, 1 over the pion mass. But you're thinking about hard processes. So this is a photon that has a large virtuality, right? So even the photon has a mass scale associated with it, and so is going to be a short distance effect. So in what sense is the photon interaction not suppressed, while as the strong interactions are in these ultraperipheral collisions?
Just one thing to mention: these photons are the Q squared is very small. They are like quasi-real. It's almost real photons that we are hitting in these UPC processes. And so, but the the electric field or the electromagnetic field, it has a larger radial extent than the nucleus itself. So then it can really happen like this, that the impact parameter between the two nuclei is so large that the strong interaction is just not able to cause any interaction. But then the electromagnetic field extends to much larger radii. And so then this in these events, when the impact parameter is large enough, this is then allowed.
I see. So the interaction is hard because this very, very nearly on-shell photon is tickling a quark that has a large fraction of the momentum. Is that the right way to think about it?
Yeah, exactly. So and then of course, in addition to have like this trigger that we have a UPC event, if we want to study like hard interaction, there has to be some scale. It didn't come from the photon, and the quark, of course, is also on shell in the on shell in the collinear picture. So then it must be the final state observable that is providing the hard scale. So in this case, it is the jet that is providing it. So only if we require like a high PP jet or other high scale observable, then we are then we have a hard interaction in the process.
Super, thank you. I think Herbert, you want
I already have my questions on that floor.
to? Any last? Yeah.
I'm still a little confused with this ultraperipheral. Like the diagrams you drew, essentially they look like similar to, you know, the regular. I don't know. How is it different from just giving the lattice scattering? I saw one pattern you had leaving. There was a gluon kind of coming out. And
this is clearly dirtier, right? Because you have nuclei on both ends. Yeah.
Sure, yes, okay. But then
And then also in DIS, the photon is highly off shell, and that provides the scale.
What makes these ones close to on-shell?
Uh-oh. Oh. I didn't like your question. It was a tough question, though. He bailed. I mean, I think the point is that it's precisely this very large distance that forces it to be nearly on shell.
Oh, they have to go very like this.
Yeah.
But surely these should be like super like rare things to happen, right?
I think so, but I think you also get a boost because of the Z factor. So you have this huge number of protons that gives you a lot of field. Yeah. But I guess I'm still a little confused like you. So he said, okay, so it's nearly on shell, and the scale isn't caused by the quark, it's the jet, the dijet. So somehow you have something nearly on shell, something that's nearly on shell,
and you give it.
And it somehow has a huge. I don't. That seems very rare. I think
it does seem like it's reasonably rare.
Yeah. But I guess everything is rare because it drops like whenever some power and scale.
Seems to have trouble coming back in.
Yeah.
Also, I thought like the leading order contribution to this JPSI production and so forth would be, I don't know, so you just got like a bunch of photons and then you draw like a kind of a quark little
Right. Yep.
But it was, I don't know, so I'm a little surprised to see what look like something's coming out of the nucleus, like it's breaking apart or something. So that's a little.
Yes, I think that just looks like the standard hand-back diagram from one side.
Yeah,
it just flipped. Yeah.
So photon coming in.
Yeah.
And then I guess
so the gluon contribution is just you pick up a gluon essentially. And to pick up the gluon with the photon, you need to split the cubic bracket. You need to have
that's
a
not
cubic box.
Yeah.
Very good.
This is a bit like well, TIS.
NLO.
NLO when you start talking to blooms. At least at the bottom end of the diagram, right? And then you have a similar thing on the other side.
But I think that these Quarkonia production cross sections are not really very well understood by anybody.
Yeah. Oh, okay.
I mean, this is exploring the territory. I mean, people have been talking about this for a while. It's still by no means settled.
And what is it? Just like more being produced than expected or something? Or?
I'm not sure if it's more or less. Yeah.
Oh, okay. Yeah, because
I'm just checking to see if it's. Yeah, my internet works just fine.
Yeah, it's not us.
No, it's still recording to cloud. So
Oh, all right.
Yeah.
Hey, welcome back.
Hey. I'm not sure what happened, but well, anyway.
So Melinda, you were asking about
why the photons are almost real, but I think I got the answer. We had a discussion.
we got that.
Okay.
But then your further was the question about
these rare events that
Yeah.
right. I mean
it seems like it should be like a very rare thing to happen. Right?
Yeah. So I think they are, but in since you have this heavy nuclei, you have like a very large charge number in them. So then actually the electric field is quite strong, and actually you get like compared to proton-proton collisions, you get additional enhancement in the UPC cross section. So
everybody is essentially.
Yeah.
Yeah. So then actually it has been possible to measure good data sets in the LHC with these processes, like this digit data set. They are going to the data is like triple differential, and to do that you really need large enough data set. So
So yeah, I mean, this is an experimental kind of question. So ordinarily, how do people know what the measure centrality? Right? They just look at the multiplicity, and then I mean, with these kinds of impact parameters, like how sure are people that you're really ultraperipheral?
yeah. So what is done is that you require that there is some rapidity gap in your detector where there is no activity. Okay. And you also require that usually when you have like a hadronic collision between the two nuclei, then the nuclei break apart and there are huge bunch of neutrons in both directions of the collision, which you observe in the forward instrumentation. So now in this case, you require that you don't see these neutrons. So then you know that, okay, the nucleus that was going into that direction, it stayed intact. Nothing happened to that. So then the impact parameter had to be large enough so that the nucleus didn't break apart.
Oh, okay. Really good. Yeah.
Super. Okay. Well, thank you very much for a very interesting set of talks and for taking all of this time to talk to us. It's been really valuable and exciting discussions in this setting and then also after. So thank you very much. And yeah, let's thank our speaker one last time.
Very good. Thanks a lot.
And have safe travels and a great talk in Houston.
Yeah, great. Okay. Talk to you again.
Super. Thanks.
Absolutely.
Bye.
Bye.
Bye.